Hello everyone, I am Zach Peterson. Welcome back to my channel. Today we're going to be looking at a viewer question on one of my recent videos, all about what happens to differential impedance when you add length tuning structures into a differential pair. Now, if you're familiar with high-speed PCB design, you will know that differential pairs sometimes require length tuning in order to keep the signals synchronized in time. That way they arrive at the differential receiver at the same time. But of course, one common question that I get when working with new designers who want to understand more about differential pairs is, how does the length tuning structure affect the impedance? That's what we're going to look at in this video. We'll take a look at that viewer question, and then we'll look at some examples in Simbeor. Let's go ahead and get started. So before we hop on the whiteboard and explain length tuning structures in differential pairs, let's take a look at that viewer question. This question was left on our odd mode impedance versus characteristic impedance in differential pairs video. Let's take a look at the question right here. Hi Zach, thank you for the great explanation. One thing you missed to mention: if there is line matching needed, then the lines would be straight parallel lines going together, so the calculation of Z odd, or the odd mode impedance, would be affected, or would it not? So that question comes from our super fan, Mohammed Yeti, coming from the Altium Academy channel and then migrating over to this channel. So thank you very much if you are an Altium Academy viewer and also watching this channel. Now back to the question, will the presence of a length tuning structure impact the odd mode impedance? The answer is yes, it's always just a matter of how much. Now, placing a length tuning structure, of course, is necessary in some cases where you have a length mismatch or a delay mismatch for the signals or the opposite polarity signals on a differential pair, and you need the length tuning structures to bring those signals back in line. That way they arrive at the receiver within the same time window. But an important thing to understand is that the presence of a length tuning structure does impact the odd mode impedance, and it creates something called mode conversion. And it's really just a matter of how severe is the impedance deviation and how severe is that mode conversion. So first, let's jump onto the whiteboard. We'll look at how the odd mode impedance is impacted, and then we'll take a look in Simbeor and we can actually see what mode conversion is and how it's calculated. So in the previous video that's linked in the description, I did go over all of the fine details of what determines the odd mode impedance in the differential pair. But what I want to do first is just review what happens once we have a differential pair, and then what happens when we add in the length tuning structure. So if you look at, for example, the cross section of a differential pair, we have a plane down here. We have two traces up here. So this is basically microstrips. And then we have some spacing right here, we'll call it S. Now that spacing determines the mutual inductance, L sub M, and the mutual capacitance, C sub M. And the lossless impedance is then Z equals square root of whatever the self-inductance is for one of these traces minus the mutual inductance divided by the self-capacitance plus 2 times the mutual capacitance, okay? So this is the lossless odd mode impedance. Very simple to understand. And then of course, the differential impedance, we'll call it Z diff, is just equal to 2 times Z odd, okay? Now you know everything about the impedance. Now, of course, there are loss terms here in the odd mode impedance. There is the copper loss due to the skin effect and DC resistance, and then there's the dielectric loss. So those appear in the numerator and the denominator, and they do deviate from this very simple value that is independent of frequency. But we often have solvers in PCB design software that are basically calculating this value or this value when you're designing differential pairs. So these are a good starting point for most applications. Now, in order to answer the question of what happens when we have a length tuning section, we need to know what happens when we modulate the spacing, because that's essentially what a length tuning section does, is it's a change in the spacing over the length of the route. So if I just look overhead here at this differential pair, you will see that we have one of our traces and it's mismatched in time from the other trace. And so we would basically add in something like this kind of sinusoidal length tuning section. Obviously, this is not a very good drawing, but you get the idea here. You basically add in this length tuning section. And in the process of adding in this length tuning section to compensate the time mismatch, this spacing will deviate along the length of this route. So here you have a larger spacing, we'll call it S prime, that's different from this spacing. So how are S and S prime different? Well, of course, S prime is bigger than S. And as we increase that spacing, what happens to these two values? Well, these two values depend on both the distance to the ground plane as well as the spacing between the pairs. And so as you space these two traces out, what you'll see is that as S prime goes up, then LM and CM go down. Now in this region here, when you have the traces closer together, you'll have an odd mode impedance that we'll just call Z1, okay? Here in this region, you'll have another odd mode impedance, we'll just call it Z2, again, just for simplicity. So how do these two values compare? Well, in this case, Z1 is going to be less than Z2, okay? So because you're varying the impedance along the length of this trace in the differential pair, you're getting a variation in the differential impedance along the entire length of this route. So you might be wondering, okay, that's all good and well, but why does that matter for signal integrity? Well, it matters for two reasons. The first reason is that if you have a pulse traveling in right here and it encounters this length tuning section, it encounters an impedance discontinuity along this part of the route. So there is an input impedance, we'll call it Zin, looking along the length tuning section. And of course, if you have this input impedance and a signal travels along and encounters this input impedance, there can be a reflection right here. So there's some slight reflection that happens right here at this interface looking through this length tuning section. And that reflection can continue right here at this point and right here at this point and so on and so forth, wherever we have these impedance deviations. So you get these reflections that happen as the signal starts to travel through this length tuning section. Now something else happens that's very important because these length tuning sections actually create something called mode conversion. So you might be wondering, what is mode conversion? Well, normally when we send a signal along a differential pair, we say it's in the differential mode. And that requires that the signals be equal and opposite polarity, and they're synchronized as they start to enter this length tuning section. But what if I had some noise, let's say some common mode noise, so equal polarity, equal magnitude noise on these traces entering this length tuning section? What happens to that noise? Well, here, this equal polarity noise on both traces now becomes unmatched or unsynchronized in time. So now I get differential noise that exits here. So I basically get some Vn and then some Vn prime. So now I have differential noise that exists between these two pairs. Ideally, if we have common mode noise that enters a length tuning section or is on a differential pair, we want it to stay as common mode noise at the output of the differential pair. And the reason for that is the differential receiver can kill this common mode noise because differential measurements basically take the difference between these two signals and that cancels out the noise. That's the whole point of using differential pairs. It's one of the major points of using differential pairs. So that essentially explains what is mode conversion. It is a conversion between common mode and differential mode signal, or vice versa. If I send in some differential signal right here, I get out a little bit of common mode signal at the other end. Well, why does that matter? Well, if I send in a signal right here, such as a signal that's supposed to be a logic signal, I want it to arrive at the receiver as a logic signal. The problem is that some of that signal gets converted to common mode noise. And what does the receiver do to common mode noise? It destroys common mode noise. So that's why we want to limit the length of these length tuning sections as much as we can, or we want to limit their usage. And it's because they basically create losses in your signal that you're trying to transmit along the differential pair. So now we have to ask, well, what is the frequency range where this matters? How much of the signal does it actually destroy? How much of that common mode noise actually gets converted into differential mode noise? So for that, we can use simulations and calculate the mixed mode S parameters. So first, let's define the mixed mode S parameters before we get into a simulation. So to fully understand mode conversion, we need to apply differential pair concepts to the standard S parameter formalism. So with an S parameter formalism, we're basically looking at a device under test. In this case, that device is a differential pair. And we have some reference over here. We have another reference over here. And then here we have a port. We'll call it port 1. And then we have port 2. So the port in this case is basically a differential input. So we can input differential signal and we can get out some differential signal. But as I mentioned previously, in that example with inputting noise and signal and getting out the other mode, we can input differential signal but get out common mode signal, and vice versa. We can put in common mode signal and get out differential mode signal. So to quantify all of this, we have a matrix, just like we have with the standard S-parameter formalism. But instead of having a 2x2 matrix, we have a 4x4 matrix. So in the top left quadrant of our matrix, we have our differential in, differential out section of the matrix. So this basically means I put in some differential signal or noise and I get out differential signal or noise. And the S parameters are written pretty easily. We just write SDD11. So this is our return loss for differential input. So basically this means if I put in some differential signal, some of it reflects and I get differential signal reflected back out. Then we also have SDD21. This is basically an insertion loss going from port 1 to 2. Then we have SDD12. This is also insertion loss, but traveling from port 2 to port 1. And then we have an SDD22, right? That's also a return loss term, but it applies here at port 2. So I put in some differential signal at port 2, and differential signal reflects back out at port 2. So what is this lower right quadrant? Well, this lower right quadrant is for common mode in, call it COM in, and common mode out. So basically, if I send in some common mode signal, I get out common mode signal. So we would write this SCC11. This is a return loss term. And then here we have SCC21 and SCC12. These are our insertion loss terms. And then we have SCC22, also a return loss term, but applying at port 2. So what about these off-diagonal quadrants? What do these quadrants represent? Well, here in this quadrant, we have differential signal in, but common mode signal out. So I put in some differential signal, but I get out common mode signal. So we would write these S parameters in the same way. We would write this one as SCD11. So in other words, I put in some differential mode signal, but some common mode signal reflects out. Here we have SCD21 and then SCD12. Again, these are insertion loss terms. So I input some differential signal, I get out some common mode signal, and then that common mode signal is attenuated compared to the differential signal I put in. Then we also get SCD22. Same meaning, but again applied at port 2. What about this quadrant? So this is just the opposite of this lower left quadrant. This is common mode in, differential mode out. So I put in some common mode noise or signal, I get out differential mode noise or signal. Here we have SDC11, here we have SDC21, SDC12, and then SDC22. So these are the full 16 items that we would use to quantify all of the mode conversion behavior in a differential pair. That's obviously a lot of different terms, and you don't have to go through and calculate all this stuff by hand. A simulation application will give you each of these items if it can simulate mixed mode S parameters. And so of course, ANSYS can do it, HFSS can do it, and Simbeor can do it. Now of this 16-member matrix, 3 of these are most commonly used because we normally define an input, we normally define an output for a channel, and then we normally want to look at the reflection from the input, the transmission to the output, and then the mode conversion that can happen along the way. And of course, if we are putting in some common mode noise, we might want to look at how that converts to differential mode noise. And so we would then want to look at this 4th one as well. But generally, these 3 are the most common S parameters in mixed mode S parameter matrices that you look at. Now, if you're qualifying a differential pair design against some interface standard, there's going to be some limits on the amount of allowed mode conversion up to the Nyquist frequency for that interface. Now, this applies in very high data rate Ethernet channels. It applies in PCIe. It really applies anything where you have multiple gigahertz of bandwidth required in that channel. So now that we've defined what exactly we need to look at to qualify a channel, which is primarily these three S parameters, we can go ahead and look in Simbeor at an example board, and we can do a quick simulation to qualify just how much length tuning is going to be too much and to what extent or what frequency range we really start to see an effect on mode conversion. So here I'm inside of Simbeor. I've created a dummy PCB project that basically has some microstrips and some strip lines. And I've created some microstrips and strip lines without the length tuning sections, as you can see here on screen. And then I have basically the same thing, but with some length mismatch and the length tuning sections. And we can go through and pretty quickly compare what are the S parameters in mixed mode for each of these interconnects. So let's take a look at the microstrips that you see here on screen. First, I can just select one of these interconnects and I can do a quick electrical rule check, and you can kind of see what is the differential impedance for each of these. You can see here if I just hit escape, I select this one, I can do the same thing. I can get a quick check of what is the differential impedance for each of these. So you can see that they're pretty consistent. If I then run a signal integrity simulation just based on the cross section, we can just click through the wizard here to get some quick results. And we can then see what the S parameters are for these microstrips. So the reason I bring this up is just for a comparison with what we're going to look at in the case with the length tuning sections. So here you can see that we're about negative 30 dB up to about, let's say, negative 20 or about 20 gigahertz, and then we rise up to about negative 20 dB into the 40 or 50 gigahertz range. So pretty good. If we go back here over to ERC, select this one, hit build and extract. I just click through the wizard again. It's going to go through and run on collect all these measurements, and we can do a quick comparison here. You see also these microstrips are also at about negative 30, negative 25 dB up to about 20 gigahertz, and then they rise a little bit higher. So you can see here there's a little more return loss on this pair of microstrips. This pair of microstrips does have smaller spacing between the traces. So this one is at 5 mil spacing, and then these ones are at 10 mil spacing. So you can get a good comparison here just from these measurements. So now what happens when we have the length tuning sections? Well, let's go ahead and turn off these other layers, and then we can go ahead and select each of these interconnects, and then we can run through the simulation again and see what the output is. Okay, so that quick simulation has completed, and now you can see if I bring up the S parameters, they all start to look very different. I'm going to go ahead and pin this graph. I'm going to bring up this graph, I'm going to pin it, and you can see here we have very different S parameters now when we just add in those length tuning sections. So here you can see up to a couple of gigahertz or maybe about 5 gigahertz, we got pretty much the same return loss as we had in the case without the length tuning sections. But pretty quickly you can see that that loss rises above negative 20 dB. Same thing here when you have the wider spacing, but it's not as dramatic. You can see that when we start with wider spacing in between these microstrips, we do get the increase in loss, but again, it's not as dramatic. You can see in the lower graph, we do rise above that negative 20 dB return loss mark before 10 gigahertz, whereas here, we don't get to negative 20 dB return loss until after 20 gigahertz. So that illustrates one solution to help prevent mode conversion in differential interconnects that require length tuning sections. If you start out with the traces spaced farther apart, you get smaller impedance deviation due to the presence of that length tuning section. And so to see why that is, go back to the previous video that I have linked in the description on odd mode impedance. If you place the traces farther apart, you use wider spacing in between them, then the odd mode impedance of each trace will be closer to the characteristic impedance of each trace, and you'll get smaller impedance deviations once you put in a length tuning section. Let's also look at the insertion loss for these two interconnects. So if I bring up the insertion loss and I pin it, and we'll go ahead and move this down over here, and same thing up here. I bring up the insertion loss and I pin it. You can see here that at about 28 gigahertz, we have negative 2 dB of insertion loss in the traces that are spaced 10 mil apart. But when we have the traces spaced closer together, you can see here we get an additional dB of insertion loss at the same frequency. So that's partially because of the greater mode conversion, but it's also due to the fact that when we put the traces closer together, they have to be narrower, so we get a little bit more copper loss as well. Just for comparison, if we bring up the insertion loss in these curves here, you can see here, if I just bring up these measurements, that we already have -1 dB of insertion loss at 28 gigahertz in the widely spaced traces. And if I bring up the other ones, you can see here, we have also about -1 dB at the same frequency in the traces that are spaced closer together. So we still get some pretty good results here that illustrate what happens when you add in that length tuning section. It does add into the insertion loss as well as the return loss. So now let's look at what is the mode conversion S parameter for this interconnect. So first I'm looking at the pair of traces that have the narrow spacing. And if we go through, we build a quick simulation, we just click through the wizard, go ahead and hit finish. We'll go ahead and we'll grab the insertion loss plot. And just for comparison, I want to put the common mode output differential mode input S parameter here on this insertion loss plot. So this is basically going to measure the amount of signal that gets converted to common mode noise at the output of this interconnect. So here we're just going to select the 4-1 S parameter. So you can see here I've already brought in row 4, column 1. That is the SCD21 S parameter that I had on the whiteboard. And we'll go ahead and hit finish. And you can see here it comes up as this lower red curve. And so you can get an idea of just how much of that noise gets converted into common mode noise and at what frequencies this really starts to matter. So if you look down here below about 5 gigahertz and all the way down to about 1 gigahertz here down at the lower end, you see you get -70 dB of mode conversion. Practically none of the differential signal actually gets converted to common mode signal and then gets destroyed at the differential receiver. However, when you start to look over here in the mid-range at about, let's say, 35 gigahertz, you can see that you get about 5 dB of mode conversion. So about 5 decibels of that differential signal gets converted into common mode signal and then gets destroyed at the differential receiver. So this is one of the reasons that you see this peak in the mode conversion curve tend to coincide with the insertion loss curve. It's because the insertion loss curve is essentially measuring the loss in the differential signal, and it is this common mode conversion curve that explains why that happens. The other reason this is important is because if we were to place this signal onto a cable and we had a lot of mode conversion from that differential signal into common mode signal, that could create a radiated emissions failure. The limits on common mode currents on cables are actually very low, and if you had a lot of mode conversion from a differential signal into common mode, and that common mode signal got out onto a cable, that's what could then create a radiated emissions failure. Now, what about our other interconnect? What about these microstrips that started with larger spacing? Well, here I can go through, do a quick build and extract, and then I'll add in the row 4, column 1 S parameter into that graph, and we'll see what the mode conversion looks like. Now here you can see the insertion loss plot if I just bring it up and maximize it, and you can see about what the loss was at 28 gigahertz. You can see it's basically -2 dB across the entire line. But here, when I overlay the mode conversion S parameter, that same SCD21 S parameter, we basically see the same thing, but not as severe. You can see that the peak mode conversion is just a little less, about -7 dB or -6.87 dB here at the peak, around 37 gigahertz. So you do get mode conversion, but not as bad as in the previous case where we had the traces initially spaced close together. You can also see that this corresponds to the dip in the insertion loss curve, and so it also explains why you get greater loss in the differential mode when you have mode conversion. You're basically converting some of that differential signal into the common mode, and then it's going to be lost at the receiver. Now, I'm not going to do the same simulation at this time for the strip lines, but you basically will get the exact same results that you see here for microstrips. Now, here we looked at conversion from differential into common mode, but we would also expect the exact same results in reverse. If we put in common mode, for example, common mode noise, and then we get out differential mode noise. So we could also look at that by plotting the SDC21 S parameter on this plot for comparison. Again, I'll leave that up to viewers who are interested. And if that's something you're interested in, let me know in the comments. Thanks for tuning in and watching this video, everybody. I always love getting your comments and questions. So of course, if you have any comments or questions, leave them in the comments section. You can also find me on LinkedIn and send your questions there. Make sure to hit the like button, hit the subscribe button, and I'll see you next time, folks.